This paper is about the response time of a queue with speed control on the server. The speed is controlled by measurements of utilization, which control the speed in steps up and down. The bit of idea is that at low loads, the response time will follow the low speed response curve. For heavy loads, it will probably follow the high speed response curve over here, but in between, we need to find out how it makes the transition from one to the other. The results are interesting. They depend on the length of the averaging interval for the utilization delta. For very short averaging intervals, it's not very interesting. We get the maximum speed most of the time because it can shift down very quickly to maximum speed. At intermediate intervals, we get a very nice level response time for intermediate settings of the target utilization. But for long averaging intervals, we get more accurate estimates, but we get longer delays and we get this wild behavior.
Welcome to our work about service demand distribution estimation for microservices using Markovian arrival processes. In this work, we first present a closed queuing model for microservice and characterize the service demand of the queue node with APH distribution. We then model the departure process at the queue node as a map in which the parameters of the service demand can be exposed. The service demand distribution can be then estimated with maximum likelihood based on the inter-departure times. We applied two methods to solve the optimization problem. The proposed heuristic method can efficiently reduce the computational cost and yield a better performance on fitting real traces.
Hello, my name is Qest6 and this is a promotional video for the paper titled Performance Analysis of Work Stealing Strategies in Large-Scale Multi-Threaded Computing, which I wrote with my PhD advisor, Benny van Hout. In this paper, we focus on a certain class of multi-threaded computing systems with work stealing. These systems are complex systems with coupled queues and thus are impossible to study exactly. To study the performance of these systems, we therefore approximate them by a single type of quasi-birthdead Markov chains. We use analytical methods to study these QBDs. We run simulations to show that as the number of queues becomes large, the error of these approximations tends to zero. Finally, we perform numerical experiments to examine the influence of various simple stealing policies on the mean response time of these QBDs.